My name is Hayman Aziz. This video is on quantum potential and infinity. The main focus of this video are two elements. One of them is introducing some sort of quantum potential that plays a role at quantum level. And secondly, here, the asymptotic behavior of this potential, how it behaves if, for example, some parameter gets large or becomes infinity. This video is very useful for those who would like to deepen more in understanding different approaches to quantum mechanics, and those people who are interested in seeing the application of mathematics in physics. The starting point here is there are two different worlds in one universe. The very first one here normally is macroscopic, and the second one is microscopic. In both of them, the element of the intestine is motion. The macroscopic is the world in which we are familiar with it. For example, like throwing a stone, like a car is moving, even planet motions and galaxies. All of these are in the category of macroscopic. Microscopic are at the quantum level or maybe atomic level, and even inside the atom, or maybe, for example, diffraction patterns of elementary particles. All of these are described by the principles of quantum level. Then this is classical physics model. So it means this world we explain by classical physics model, but this world, they are explained by quantum physics model. And strangely here, the formulae, the principles in which governing those two worlds are totally separate from each other. They have got two different sets of equations of motion, even two descriptions in the way in which motion takes place. Before we start deepening into the quantum part, there are few elements in which we would like to understand at classical mechanics. In classical mechanics here, what is the idea? Certainly motion is the heart of mechanics. I mean, whenever you talk about mechanics, motion is the heart. Although mainly here I mean dynamics, okay? Then the second part here is certainly once we describe the motion, we will introduce some mathematical equations explaining this motion. Then later on, we solve these equations. Once we solve these equations, the final goal here is identifying or finding displacement and velocity as function of time. Whichever mechanics which is related to motion, this is going via this route, whatever it is. Either you throw an object, for example, here, or maybe a car is moving, or maybe a shuttle is going to space. Exactly, you follow the following steps. Then, to describe classical mechanics, there is a function, normally we call it Lagrangian. Here, I'm not talking about too much the history of Lagrangian or how this was produced, because otherwise we need much longer video to do that job here. But I'm mainly extracting those elements in which they are useful for my study. Usually Lagrangian is defined by the difference between kinetic energy and potential energy. And later on, for example, here, this Lagrangian simply is function of displacement, function of velocity, and function of time at the same time. So it means any Lagrangian function here contains those elements. And here x dot simply means the velocity of the object, the moving object. Then later on, this is as an example of one dimension, by the way, and generalizing it to higher dimensions may not be too difficult. So it means extending it to x, y, and z, or maybe Cartesian or polar coordinates or spherical coordinates. This can be done quite easily. The next part here is there is a principle in which is called principle of least action. This principle of least action is a fundamental principle of nature. And then certainly mathematicians have used it in the way in mechanics here to introduce simple equations of motion. What is this idea here? The definition of action simply is the total sum of the Lagrangian over a certain period of time. For example, this is the integral of this. Then later on, if you use this principle, so if you minimize the action, simply here you can introduce some equation. It's called Hamilton-Jacobi equation. And this is the way in which the equation looks like. And again, here I'm not going to introduce the method in which how from here and these definitions you reach to here. Most of advanced textbooks in dynamics or mechanics certainly explain this equation of motion. Then the whole aim of introducing Lagrangian and later on, for example, the principle of action is to produce equation of motion and then finally solving the equation of motion. And then later on, how displacement and velocity can be identified in terms of time. Once you solve the previous one, according to the principle of action, then you will get this equation. This equation is Lagrangian equation. And again, here I'm not going to show the detail of that. Then we will use this here. In a simple word, this equation is a generalized form of the well-known equation in which we learn it from school, force is equal to ma. But this is more general. So it means simply here, if you have got a system, and if you identify the Lagrangian, which is in terms of kinetic energy and potential energy, so it means you set up the equation of the motion, and then if you have got some boundary conditions, then you solve it. Then you find out the displacement and velocity in terms of that. Then details of those derivations, as I mentioned it already here, can be found in most advanced dynamic textbooks. Examples, then motion of any object from a small piece of a stone to a large shuttle sent to the space. Then all of those can be described by the above. And all of these are assumed to be in classical levels. Then the second part of the study here is quantum level. Then when we talk about quantum level, there is a well-known equation which is known as Schrodinger's equation or wave equation. Simply here, this equation is given by this, and certainly I will shortly explain the meaning of each term from here. But certainly here I'm not going to show how this equation is derived. If you are interested in the origin of this equation, in which originally was introduced by Schrödinger, then you can find those derivations in most of textbooks in quantum mechanics. But I'm going to use this certainly here. This is simply a second order partial differential equation. So in terms of x and t, partial differential equation. And generalization of this equation in three-dimensional also is not going to be too difficult. So in terms of y and z as well, or spherical coordinates or maybe cylindrical coordinates, they all can be managed easily here. But here, for the purpose of the study, one dimension is enough for me. Then those terms in which we have here psi, which is a function of x and t, this is called wave function. So it means in this model at quantum level, we describe motion of the particle through this wave function. Or maybe we can say the particles at this level, they behave like wave. Or at least the motion of these particles have wave feature or maybe wave behavior. Mathematically here, psi of xt is a complex function, which is like this. This is a normal complex function in which we usually learn it in complex analysis. And I is the square root of -1. Then simply here, in this equation, we have got V. This V is classical potential energy. So let us be realistic. This is classical potential energy. So it means this is quite normal in which you have got a quantum particle, but this quantum particle moves inside an environment or a place in which it has got classical potential. So it means mentioning the classical potential here does not mean that we eliminate fully the classical potential energy here from this equation. The second part here is m certainly is mass of the particle, and then h bar, normally this is called h bar, is called Planck constant divided by 2 pi. The Planck constant, which is a very, very small number, and its existence is useful at quantum level. Now, problems with interpretation. Unfortunately, here during the last almost 100 years, ever since this equation has been introduced, until nowadays here, we have got few different ways in which we look at quantum mechanics. Mathematically, if you look at this equation, is a quite beautiful mathematical equation and is assumed as one big triumph of the 20th century, and then has given a big boost to quantum physics. We had quantum physics certainly before even the introduction of this equation, but when this equation was introduced, certainly quantum physics became a bit more, not necessarily clear, but it means more slightly applicable in real practice. Then has got wide applications in many fields in physics. Then does not have a proper interpretation. This is the problem with it. So it means there are debates between different physicists during the last 100 years here. What does this mean? How we interpret this? How this is going to help us understanding the quantum? No one knows it. And there are great statements by big scientists, including Richard Feynman, the American physicist, who was one of those scientists who was working quite intensively in quantum mechanics. And here he says, anyone who claims to understand quantum theory is either lying or crazy. And I think I can safely say that nobody understands quantum mechanics. So the problem of understanding quantum mechanics is not something which is easy, but its application, we use it in real practice. And then we use it in physics, we use it in chemistry, we use it in different fields of science very successfully. But what does it mean? Perhaps we have got ambiguous problem with that one. Now, Why mentioning interpretation is relevant and important here in this video? The reason is because one side of the interpretation in which is helping to understand the concept of this quantum potential in which I'm analyzing it in a little bit detail. Playing with equations. This is quite interesting. A British mathematician, his name was Dirac, in the first quarter of the 20th century, he played with equations. When we say he played equations, sometimes it happened that you bring equations and then you subtract, you integrate, you divide, you multiply, you produce new parameters, new variables, then you plug it into the main equation, and so on. He played with equations in quantum mechanics and relativity. Later on, he produced some strange and unusual solutions, in which at that time these solutions were quite unusual. Then it wasn't even clear and acceptable at the start. Even his community wasn't accepting that idea because everyone was very vague. He introduced an interpretation that every matter must have antimatter. Then it took many years later on that this theory to be proved. The reason for mentioning playing with the equation, in which we shortly show how we play with the equations in here and introduce something new. Then this is his statement, okay, in which he was playing with equations, and the purpose of playing with equations just to see, okay, what is the outcome, or can we get something maybe useful. Introducing quantum potential model. This is now the heart of our discussion. What is the idea here? The idea is, again here, playing with equations. The wave function can be written in the following way. So it means simply here a real part plus imaginary part. And later on, this can be translated into sine and cosine functions. This is a well-known structure in which we have in complex analysis. Or later on, through, for example, a relationship between S and R with F and G can be easily established. So it means these two, practically, you can relate the R to the F and G and S to the F and G, or vice versa. Then this is simply the relationship, which is fairly easy. You can just substitute it and then separate the real and the imaginary parts. Then finally here, the wave function can be written in the following way, or the wave function can be translated to an exponential form of a complex number, and this is a well-known formula in which we have in maths, introduced originally by Euler. Then substitute the above into Schrödinger equation and separate the real and imaginary parts, then you will get these two equations, because you will have only two parts. One is real, one is imaginary. But let us see the meaning of these two equations. Although in here, I mainly focus on equation number 7, and hopefully in future videos, we will bring equation number 8 and use it for its own purpose. But at least for the time being, just focus on number 7. Then, quantum Hamilton-Jacobi equation. If you look at this equation number 7, it's exactly the same as equation 3 in which we had it earlier on. But there is an extra term in which is this, h bar squared divided by 2mr. the partial differentiation, the second order partial differentiation of r with x squared. This is an extra term. And this extra term here, because everything here is having the unit of potential, then we can name that this is just a name, we name it as quantum potential. And simply here, this cannot exist maybe at classical level. The reason is because h at classical level is too insignificant and small. That's why we do not see it at classical level. Then this is named as quantum potential and denoted by Q. This is that new quantum potential, and more details about this approach can be found from this reference or any related papers written by David Bohm and Basil Hiley. Then, now certainly this Q will be quite insignificant at classical level. The reason is clear, because h is too small, and if you square it, it becomes even much more small. Behavior of quantum potential at infinity, or when something is approaching infinity. In practice, finding an expression for Q as function of x and time, like the one in which we just saw earlier on, in general form may be only interpreted as some sort of potential similar to the classical one, but it manifests itself at quantum level. So we do not have this at classical mechanics or classical level. But now the question is, what does it mean? What does it look like? And many more questions like this about this Q is still not very clear. There are a few simple things in which I'm trying to clarify in this video. And this is like a fundamental fact for any general theory. Whenever you learn any theory, although mainly I'm talking about physics, then it means the general form of the theory may not be clear, may be vague, so maybe even not understandable by normal physicists or normal scientists. But if you now produce and introduce some numerical examples, and then if you use your theory on those examples here, then the meaning of the theory may become a bit more clearer and maybe more understandable. And this is like something like a fact. This is not only in this case, in many cases. Even Schrödinger equation itself, if you are given this equation purely itself, may be very difficult to understand. But if you are given this equation here, or if this equation is used in a practical example or numerical example, things may become clear. Here I'm introducing two examples. These two examples, example number one, motion of a particle between two infinitely high walls. This is a quite well-known example in most of quantum mechanics books. So normally in any quantum mechanics books, or most of them, once we learn the concept of quantum mechanics, Schrödinger equation, this may be the first example in which is given just to illustrate how quantum or how Schrödinger equation is used at quantum level. The idea is simple. So this is a particle, and this particle here is moving between two infinitely high walls. Then the potential, the classical potential, is zero anywhere within the box. That's why sometimes, for example, we call it box. And especially here, if we extend it to 3-dimension. And then outside the box, the height of the wall is infinity in either sides. So maybe diagrammatically, this may be interesting. So it means this is the x-axis, and then the length of the box is from 0 to L, and the particle is just moving within here. Then these are the two infinitely high walls. The reason for assuming infinite height is so that this particle has got no chance to go outside. So the particle cannot exist apart from this region between 0 and L. Then in this case, if you use your Schrodinger's equation at least between 0 and L, the Schrodinger equation now reduces to the following, because we removed V. And now the question is how we can solve this. If we are well familiar with solving partial differential equation or some groups of partial differential equation, there is one type of solution in which you can separate the x component and the t component product of them. And then certainly here, if you use those here, you will get easily that the function of time is this, and this is the function of x. You can substitute it and you can easily check that. Then the next part here is the focus on the function part, which depends on the x. This satisfies, if we substitute it back into the previous Schrodinger equation, then will be this equation. And this equation is a second order differential equation. Solving it is not too difficult. So it can be solved by normal methods through auxiliary equation, although I'm not showing it here because it takes a few steps here. But the solution finally looks like this. Then definitely here the reason for the sign, because boundary conditions being used. So what does that mean? It means the function is 0 at x equals 0, and the function is 0 at x equals L. Then due to the fact of the nature of sine and cosine, then it means it can be possible at 2 pi x or 3 pi x or 4 pi x and so on. Then that's why the function has got states of solution, not just one, has got many different solutions for different ends, infinite number of solutions practically. And then even combination of all of those will also be solution. The main part in which we need here, okay, this is the energy state. So it means energy 1, energy 2, energy 3, because the energy of the particle in this box here can have discrete values. Then the quantum potential calculation will now be easy because R will be this part according to the original definition of the wave function. And then if you substitute this back into the formula we introduced for the quantum potential, then it means the value of the quantum potential now will be this. Okay, so now we will comment shortly here on this value on the next page. There are a few important points on this quantum potential. One of them is we assign state in the same way as we assign state to the energy. This has got state as well. It means for n equals 1, n equals 2, n equals 3, and so on. Because this quantum potential here for different states apparently seems to be different from the classical version here. It does not possess continuity. The second point here is this energy state, for any energy state from the previous equation, it doesn't seem to depend on position. So it means anywhere between or anywhere inside the box, this quantum potential has got one value. It does not change. It's not like a normal classical potential. Then if the size of the box becomes infinite, you notice from the previous expression in the previous page that quantum potential for any n will approach zero. So it means the system then becomes classical, and any quantum feature will disappear. So it means simply here this can be extended to a 3D box, as I mentioned it earlier on. Then there may be a little interesting point. So it means the behavior of this particle here at large scale is classical. Perhaps this is the fact that the universe at large scale behaves in classical rather than quantum. Now, the second example. The second example is, again here, a well-known example we have got in quantum mechanics. This is called quantum harmonic oscillator. And this is extracted from a normal classical harmonic oscillator in which its equation looks like this. And again, here in many textbooks of dynamics, we have got this equation. I'm not going to show how this equation is derived, but simply here this is omega, in what is called angular velocity, is defined in terms of k, which is spring constant, and mass, which is attached to the spring. And then E here is assumed to be the total energy, which is the kinetic energy and the elastic potential energy. This example is an example in which is well known as SHO, simple harmonic oscillation. But definitely this is not a spring. It means it's not the only mechanism in which it behaves in this way. There are other phenomena in nature in which they have got the same feature, or may be described by similar to this equation. And this is going to be the total energy in which we have kinetic and elastic potential energy. But now the main point is we need to talk about the quantum part. So what is the quantum part? If we introduce Schrodinger's equation with this new potential, then it means now the Schrodinger equation looks like this. But this equation, if you look at it here, is quite different from the previous one because it's not very easy. The reason is because you have got x squared and then variable parameter. But at least this partial differential equation may be solvable by product of x component and time component. And this helps. Because if we do the same thing here, and then if we substitute this, differentiate, separate the x's, separate the t's, then for the t part, you will get the solution. Exactly the solution has got energy states, but the expression is different. And then at different levels, n equals 0, n equals 1, n equals 2, and so on. Then the x component part forms this differential equation. Then solving this differential equation is not going to be easy because the reason is this coefficient here is not constant. But if you look at mathematical references here, solution of this can be achieved through a polynomial which is called Hermite polynomial. And this Hermite polynomial is simply math, but it's helping here a lot. So it means the solution of your function here is taking this form. And this is the Hermite polynomial. So Hermite polynomial has got different functions for different n's in which is displayed shortly here. Here for simplicity, alpha in here is in terms of the variables in which you have or parameters in which you have in your model: mass of the particle, omega, and h bar. Then this is a constant which is more or less related to normalization of this function, but obviously here in this study, I'm not touching this part at all because it doesn't play any role for my purpose. So it doesn't matter. You don't need to worry about it. But this can be calculated, certainly. And these are some quantities and their units. The advantage of those in which you will see it shortly here so that you can arrange the value of Q according to proper quantity units. This is list of Hermite polynomials. Certainly, if you look at mathematical references, perhaps you may have got not H4, H10, H11, and so on. But again, here, I cannot write all of them here, definitely. And there are some useful differentiation relationship between these Hermite functions, in which you can even introduce them very easily here. This is the first differentiation, and this is the second differentiation, and these will help in calculating the quantum potential in the next slide. Calculation. So now certainly you go back to your original function in which you found it in terms of the second differentiation, and then this time here, because you have got Qn, definitely you'll have Rn, and Rn is given by this. From your solution of the differential equation. Then if you take the first differentiation, it looks like this. If you take the second differentiation, it looks like this. Okay, then the second differentiation can easily be even simplified in the following form, and I strongly advise, especially those students who are interested in those, pause the video and then try to rederive those by yourself so that you train on using those equations. And then your quantum potential, now the quantum potential at any n state, practically, can be given by this formula. This seems to be a new formula. And then definitely here, this formula is only valid when n is greater than 1. So it means from 2. So it means you can't substitute n equals 0 and find q0. Then q0 and q1 would have to be calculated separately. This is q0 and this is q1. But these now become the base. You can find the others in which they are shown in the next page here. So this is q0, this is q1, this is q2, this is q3, okay, q4 and qn, by the way. And then I introduce two parameters here in which one of them is lambda, gamma, and this gamma here is quantum potential constant given or defined in terms of h bar, a, and m. And this is quantum potential factor, this part. And then if you draw those, then it looks like this. This is n equals 0, n equals 1, n equals 2. Then definitely here I don't need to draw all the others, but apparently now the pattern seems to be clear. So as the energy level n becomes larger, then you notice that the effect of the quantum around closer to the value of x equals 0, or in this domain here, becomes more significant. So it means at higher energy levels, the system can experience or experiences more in quantum environment. Other aspects of quantum potential. So far, for example, in this discussion here, this Q is assumed to be positive, at least in the two previous examples in which we have introduced. But there are a number of interesting questions on this quantum potential. Classical potential can be negative. Can Q become negative or behave like negative? So these are some questions in which I will leave for future videos to be answered. Then in classical mechanics here, potential difference between 2 points can be calculated by the difference between these two potentials, or the difference gives the kinetic energy. But now the question is, do we have a way, or do we have a statement that quantum potential difference? So what does it mean? Classical potential exists regardless if there is motion or not. But this is not the case maybe in the case of quantum potential. So apparently here, if you do not have quantum particle here in motion, maybe quantum potential does not exist. Then, does quantum potential have a physical reality, or it is just a model postulated to explain some physical phenomena? We don't know. And more other questions. My special thanks to Professor Alan Payne, who helped me a lot in preparation of this video, and his valuable comments. The end does not seem to end. Thanks for watching.